Ladies and gentlemen, welcome to Bahrain Chemical Engineers LET webinar. My name is Fatma Hussein, Senior Process Engineer from the Bahrain Petroleum Company, and it is my pleasure to be your moderator tonight. This webinar is brought to you by BChemi. BChemi is the national platform for chemical engineers here in Bahrain. It was established in 2018, and since then we have been providing opportunities for seasoned and young professionals and students, such as organizing co-located events and regional conferences, and providing industrial summer training for the students, as well as providing technical seminars such as this one, the LET webinar. LET stands for Lead, Inspire, and Transform. And in today's world, leadership in innovation and transformation is a must in order to stay ahead and be competitive in all fields. And as we, chemical engineers, we do like to troubleshoot, optimize, come up with innovative solutions to tackling today's world problem. And tonight, we will get to hear from an expert on an innovative way to produce renewable energy. We do know that in the future, the demand on renewable fuels will drastically increase due to not only the environmental impact, but as well as the legislations that are being imposed by major countries. There is wide variety of available renewable feedstocks, such as virgin oils, animal fat, solid municipal waste, which can be converted into diesel and jet fuel. And in today's webinar, we're going to get to hear all about this, the chemistry involved, the challenges that's facing it, and the technologies that are available to convert bio-waste into fuel. But before we begin, I would like to remind you to switch off your mic and video at all times, excluding the speaker, of course. You can click on the hide non-video participants on your top right corner so you can have better view of the speaker. Please ask your questions in the chat box so I'll be able to see them and then direct them to our speaker. And at the end in the Q&A, please feel free to raise your hands, and this is when you can unmute yourself and ask questions directly to our speaker. We're excited to hear from him. So our special speaker for tonight is Sylvain Verdier. Sylvain has been working with hydroprocessing for the past 15 years, and he has been focusing his efforts on producing renewable fuels for the last couple of years. He holds a master's degree in chemical engineering from the University of Pau from France, and a PhD in chemical engineering from the Technical University of Denmark. He joined Topsoe in 2006 and is currently working as a senior business strategy manager of innovation and strategy team at Haldor Topsoe, Denmark. Sylvain, it's wonderful to have you here with us tonight. How are you?
I'm good, Fatima. How are you?
Doing pretty good, thank you.
Good. First of all, before we start, thanks again for inviting me and to you and to BChemi. It's a pleasure, and yeah, I'm looking forward to talk about renewable fuels today. Should I start sharing my screen, Fatima?
Yes.
Let me know. Good. Let me see how that works. Yes. And you should be in presentation mode now. What are you saying, Fatima? Up, swap. Yes, and this should work now.
Perfect.
So we have about, how long do we have, Fatima? 30 minutes, give or take, something like that. Normally we can take we organize some seminars about renewable that takes 3 days. So to cover this topic in 30 minutes is going to be challenging. I have a lot of slides, but I'm doing this for you. So please ask a lot of questions. And I think we have a range of students, people with more experience. So we try to cover the different topics, but we try to make it as interactive as possible. And I speak normally quite fast. The accent, there's not much I can do about it, but hopefully you understand me. And then, yeah, but feel free to ask questions. And Fatima, you stop me with respect to time. So for those of you who will leave the webinar before the end, we basically start with a take-home message. So the 3 points I'd like you to remember when you stop today, when you leave this webinar, it's chemistry is key, know your feedstock. It's really a lot about feedstock, and as chemical engineers, we like chemistry, or we should like it to some extent, and so this is quite central. Know your feedstock. Yeah. Number 2, feedstock supply is challenging. Yesterday, for example, I had a meeting with customers, and the project is basically just depending on feedstock supply. If they can get a feedstock, they will proceed with building a HVO or SAF plant. If not, no project. So it's really about having the right feedstock. And therefore, you might not get the feedstock you want, and process flexibility is crucial. And if you have the feedstock, basically, we have solutions for you. So we have the right process catalyst. We can produce renewable jet fuel and diesel. I'll touch upon briefly about renewable naphtha. Marine biofuels start appearing, but yeah, I don't think it's quite there yet with hydroprocessing. But anyway, this is a take-home message. I'll go very briefly talk about Topsoe, my company. So Topsoe was created about 8 years ago by Dr. Haldor Topsoe. He passed away some years ago, unfortunately, but the company is still owned at a large majority by the Topsoe family. So we are based in Denmark, and I've been living here for 20 years now. There's a heat wave today, by the way. Fatima was laughing. It's around 28 degrees here in Denmark, and we cannot take it. We're not used to it. But joke aside, based in Denmark, we have factories in the US for catalyst and in Denmark, and we have office everywhere, including one in Bahrain, and I'm greeting my colleagues who might listen now. Yes, we got a new CEO about a year ago, and the whole strategy changed to the company. Of course, we continue with fossil, hydrogen, methanol, ammonia, sulfuric acid, and so forth, but we are moving towards a lot about working on decarbonization technologies. And today we'll talk about one, which is how to produce biofuels. And we still have a lot of resources within R&D. Around 8% of our income of revenue is used for that. We do licensing, engineering, and so forth. A lot of catalysts. I skipped this. Today we will talk about biofuels. Maybe we'll have another webinar at one point about hydrogen or green ammonia and methanol, all these other technologies and products we can help you with. But today, let's talk about biofuels. So let's go. If you're not familiar with biofuels, you will discover a whole world of acronym, of abbreviation. So I tried to summarize the main ones, or not the main ones, but some of them to start with. So you have what you might be familiar with, which is biodiesel or FAME, fatty acid methyl ester. So you take, let's say, virgin oil, you do trans esterification, and you take biodiesel. In Europe, you can blend up to 7%, depending on the country. Yes, you have different rules. Some countries like Brazil be 20, and some countries like Malaysia, Indonesia are talking about increasing to higher levels. Then we have HVO or RD. So HVO stands for hydrotreated vegetable oils. In Europe, that's how it's called normally. And in the US, it's more called RD, renewable diesel. But let's say I'm using animal fat. Will it still be called HVO? Yes, it will be. So yes, HVO, it's a generic name for you do hydrotreat or hydroprocess some fatty acid-based feedstock. And the third acronym we should look at is dedicated to jet fuel, renewable jet fuel. So one is SAF, Sustainable Aviation Fuels, RJ, Renewable Jet Fuel, and SPK for Synthetic Paraffinic Kerosene. I know it's a lot of abbreviations, but just wanted to start with this. For some people, HVO and biodiesel are the same. For us, it's quite different. One is a process of esterification, the other one is due to hydroprocessing. So it's quite different condition, hence different products. You might be familiar with this, but yeah, again, for those of you who are new to the world of biofuels. For those of you who are experienced process engineers, you might think, okay, renewable fuels, it's a bit like fossil, I just need to process something else. It's actually a very different world. When I started, I worked about 10, 15 years on a residue and hydrocracking and so forth. So moving to renewable fuel was quite an interesting transition. The complexity is not, it's just different complexity. You not only have to look about technology, you have to look at the whole thing. So the first thing is about feedstock, as I mentioned in the introduction. What is available, how much does it cost, where will it come from, and so forth, and what is the quality, which is most important. You would get batches, maybe, I don't know, 50 tons or 10 tons or whatever you can buy, and each batch will differ. So can your unit process it? Will it make the same product? How will it affect the exotherm or, I don't know, hydrogen consumption in your unit? So that's quite different. Conversion technology and cost. Pre-treatment a lot of these feedstocks contain a lot of contaminants, such as phosphorus, silicon, chlorine from table salt, if it's used cooking oil, and so forth. So pretreatment will be needed. If you have a solid waste, you might want to transform it into a liquid, a biocrude, using pyrolysis or hydrothermal liquefaction, to name a few technologies. And here, this is also a challenge. Hydroprocessing is important. Hydrogen will be key, of course, and CapEx, OpEx is obviously important. The main challenge, what I see within renewable fuel, is the whole market regulation world. We're moving toward a very regulated world in the EU for biofuels. EU, US, Canada, the UK, it's really, we spend so much time discussing legislation, blending mandates, greenhouse gas targets, because this is really what it's about. So as a process engineer, you might think it's not related to your work, but it actually will be. Even we spend a lot of time discussing this, not only with management or people looking at environmental engineers, but also with process engineers. So it's really important. Would you make renewable jet fuel, diesel, naphtha? Naphtha was not very valuable earlier, like 10 years ago, renewable naphtha. And now the petchem industry is actually quite interested in it. So the feedstock, the process will affect the product you would get, and you will have to design your process, of course, based on the specs of the product. Last but not least, it's mostly about sustainability and the whole certification issue about how to certify you have a biofuel from beginning to end, greenhouse gas calculation, life cycle assessment. It's an additional complexity, and some of your companies might not have this know-how, but they will have to build it if they move into this world of renewable fuels. So that was a quick introduction. I'm checking the time. So the agenda today, we'll talk about chemistry, as Fatima told you, challenges and solution. Of course, we don't only want you to worry. A few words about sustainable aviation fuel, because this is really, the last couple of years was really about renewable diesel, especially in US and Europe. And now sustainable aviation fuel is really taking off. So I'll talk about that, then Q&A if time allows. If not, you can always write to me, or Fatima will follow up on the questions. The main driving force, as Fatima said in introduction, it's mostly driven by legislation. So here I selected a few countries, RED 2 in Europe from 2021 to 2030. We had RED 1 from 2011 to 2020, RTFO in the UK, RFS, federal state level in the US. Some states like California, Oregon, Washington State also have some specific legislation on top of the RFS. Canada, also federal, also some states like British Columbia have something. CORSIA for aviation. We're surrounded with legislation within biofuels. And I will not bore you today about that, but that's really the main driving force behind. And it is really important that every company looking into that master this, because this is what's behind. But let's talk about, we are chemical engineers, so this is what we should talk about today. In order to engage with you, we discussed with Fatima, and we said we should do a few polls. So the first poll, and I think Fatima, people will be able to click on the screen soon, is that correct?
Yes.
Okay, so the first question I have for you is, now I cannot see the question, but I should remember it. In EU 27, so the 27 member states, what will be the share of renewable fuel in 2030? So in 9 years from now, will it be 2%, 5%, 10%, 14%, or more than 20% with the current RED 2? Fatima, I have a question for you while we wait, and I hope it's okay with you. Do you have a guess about, and it might help actually our listeners, about what was the share in 2020 of renewable fuels in Europe? Are we talking about 5%? Yes?
I live in the Middle East, so for me to
Yes, I know, it's quite different.
But okay, so I would guess it's still picking up. It has picked up, still picking up. So maybe between 5 and 10.
Exactly. So, okay, it's how do you call that? Spoiler alert for the answer, but we are around 10%, 9%. So it's average EU level. Some member states are below 5 actually, but some member states like Sweden, Finland, northern countries are much higher. And it's binding for EU level, but not for each member state. So actually, okay. And we can look at the answers. So right now, the target of the current RED 2 is 14% in 2030. But tomorrow, I'm not joking, July 14th, it's called Fit for 55 package. So it's part of the climate law. And in EU, they are going to revise around 10, 12 directives that's going to revolutionize energy and transport industry. And tomorrow, they will possibly go for higher levels. Instead of 14, they might go for 24 to 26% in 2030, in 9 years. every fuel supplier in Europe will have to produce at least to blend 26 maybe % of renewable fuels. And this is why we see it's a global phenomenon, because many already in the US, they are already exporting renewable fuels in Europe. We're also aware of projects in Middle East, Asia, Latin America, where people want to export to EU. Hence, yes, this may be relevance of this webinar today. So 14% as of today, but maybe tomorrow they would go for 26%. So let's see. It's going to be interesting tomorrow. Cool.
And I think
excellent.
most people got it right, more than 20%.
Exactly. So it's perfect. So, yeah. But as of today, it's only 14, the current target for 2030. But it's going to be increased. So, okay. Okay, next one, a bit of chemistry, as promised. Okay, let me close this. Yes. The way there's not an official definition about feedstock. The way we see it, we divide it in 3 types of generations. So you have the first generation, which is virgin oils. So rapeseed oil, palm oil, sunflower, soybean oil. Second generation, waste oils and fats. And it's a long list, but I would just name used cooking oil that you might know. Animal fat, distillers corn oil, it's a byproduct of ethanol production. It's mostly from the US. And then crude tall oil, which is a residue of a pulp mill. If you have the craft process to make pulp, to make paper later, you have the black liquor, and you can extract crude tall oil with some type of trees. And it's mostly in Scandinavia, Canada, and Russia. And all the waste from palm oil production. Third generation, here we divide it in 3 categories. Number 1 is solid waste biomass, municipal solid waste, forestry residue, and so forth. Then we have these winter crops, rotational crops, basically. So it's small now, it's a very small amount. It's mostly one company behind each project, but it could be carinata, which is called the Ethiopian mustard, or castor oil, microalgae. And then the last one, is it bio? It's not, but is it renewable? Yes, it's basically you use plastic waste or end of life tires, and then you can make pyrolysis and fuel again. So in some member states, in some countries, it's allowed. So this is basically the feedstock you have. And they might have different chemistry, but we'll focus on virgin oil and waste oil and fats because they have very similar chemistry. Basically, they mostly consist of triglycerides, which is, so you have a carbon backbone, some oxygen, and then you have a long, what looks like an alkane. And we like alkanes or normal paraffins because this is what we have in fuels. Imagine you make diesel out of that, really high cetane number, cetane index. Okay, very poor cold flow property because it's quite high, maybe 26 degrees C, but it's really good. Then and this is mostly what you have in virgin oils. If you put an oil with a bit of water, you have a hydrolysis, and you basically form free fatty acids. You just decompose your triglycerides into this, very similar structure, but this is much more acidic because of the carboxylic acid function. So this will increase the acidity. And this is more present in used cooking oil, animal fat. So this is why with such feedstock, you will have a higher TAN number, acid number. And what we don't like. So this is good. You make normal fuel. It's nice. And here, we don't like that very much. Those are, for example, phospholipids, and they contain phosphorus, which is going to kill your catalyst. You might remember stories, I've heard stories about anti-corrosion additive that contain phosphorus that kills the catalyst, or what you see in a spent lube upgrading. This is similar story. So a few ppm is enough to make a crust, and you will see a nice picture later. That's going to kill your catalyst. And those come as a salt. So you also have calcium, chlorine, iron, and you name it. So this is composition of the feedstock. So unlike fossil, which you have 1,000, if not million of compounds, this is very simple. Like to understand what is in the feedstock and the product, it's much easier than fossil. So characterization of feed and product will be less of a challenge in terms of chemistry. For those of you who don't know, for vegetable oil or used cooking oil, you don't do a distillation. What you do is a fatty acid profile. So let's go back to this one. So basically you look at your feed and you say, okay, how many C16? So this is 16 carbon, this is 18 maybe, and how many double bonds do I have? So here I have 1, 1, and 2. So when you buy your feedstock, you would get this type of fatty acid profile. Let's say you have tallow, so animal fat. Maybe you have, 16 carbon with 0 double bond, and you can have this amount, or maybe C18, and it's this. And it's actually quite interesting to know that because it will tell you what you will have in your product. If you make jet fuel, maybe you want more C16. It means less cracking. If you have more diesel, okay, it's always in the diesel range. That's okay. But let's say you buy carinata, which is a winter crop. You have a lot of C22. Is it C22 or C24? I can see C22. Yes. C22, and here this is above diesel range, so you will need cracking. So basically, and the number of double bonds will also affect your hydrogen consumption. So each feedstock batch basically will have a different fatty acid profile, but it will tell you which product you have, what is the quality, and how much hydrogen you might use. So yes, time, a bit short. I speak too much. Okay, Paul, number 2. Fatima. Okay. We talked about feedstock, the chemistry, but just maybe you don't have an idea of how much volume is available out there. So the first question I have for you, if let's imagine we forget food and feed, we don't care about using the virgin oils and the waste oil and fats for us. We have to use all of it to make biofuels. So we use all virgin oils, all waste oil and fats that I mentioned. How much renewable diesel you think we could produce? And it's really a back of the envelope calculation I've done last year. But what is the oil consumption now, Fatima? Are we around 95, 100 million barrels per day, the oil production? We're close to that, I think.
95?
Yeah, no, but yeah, around, yeah, I think so.
Oh.
I don't know. But basically, can we match that with renewable fuel? Will the world go fully out of fossil oil? Okay. Do you have a guess, Fatima? No?
Well, we do have enough biomass in the world for sure.
Yes.
But are we able to utilize it fully?
Yes, exactly. And you mentioned municipal solid waste in introduction, and that's really quite good because okay, how are we doing with time? Okay, let's look.
We're doing well. We're doing well.
Okay, good, perfect. But basically, I can tell you if we're just so virgin oils, we have around 170 million tons per year. Okay, so I said, okay, that's not, but yeah, for renewable fuels, people think, they don't think in barrel, they think in million tons or 100,000 of tons. So 170 million tons, it's around 15-20% right now used to make fuels, biofuels. And then used cooking oil and waste oil and fats, it's around 20% of this. So it's only 30 to 40 million tons per year. So all in all, maybe 200 million tons. And how much HVO is that? It's not much. It's 3.5 million barrels per day. So basically, if we're using all the virgin oils and fats, waste oil and fat in the world, we could produce 3 point something, less than 5 million barrels per day of HVO. Now, everybody wants to make SAF, sustainable aviation fuel, renewable diesel, maybe renewable naphtha. The petchem industry is really interesting in that. And there's the same feedstock. So if we tell people, if you have the feedstock, keep it and we'll help you. You have the king of the world if you have the feedstock. But as I said, as a half a joke at the introduction, we see a lot of projects that don't proceed because they don't have the feedstock. So that's really the main critical thing. So, and people will have to buy cheap, nasty feedstocks. It's a bit like similar to opportunity crudes. Like you would buy nasty crudes and or not nasty crude, nasty feedstocks, and not what you want, and a lot of waste and residues, and by definition, that's limited amount. So that's why we do a lot of work, and I won't talk about that today, all the advanced biofuels. So take a waste, solid waste, and how to make fuels out of that. And we started about 10 years ago on this, because that's really what that the world will need. Okay, so the answer was, go ahead, Fatima.
Our audience are optimistic.
Yes, I wish there was more feedstock, but we will have more projects, even more, but that's really limited. It's less than 5, I'm afraid. So it was just to give you an idea of volumes, what is out there. So fossil oil will continue to be used, obviously. So you won't be out of job tomorrow, just so you know. Okay, chemistry again. So you have these fatty acids. So you remember the carbon, I think it's here. So you have this carbon backbone, this propane, backbone, you have the oxygen. But basically, even if you have the best catalyst and everything, you will have a yield loss of your feedstock. So if you buy 100 tons, you will lose, how much oxygen is there? It's around 11-12%. So that will go, like you don't want oxygen and you cannot have oxygen in your product. So if you want to use more than 7% and so forth. So basically you will lose at least the oxygen. But the first thing that goes is a propane backbone. So this will go, so you will produce a lot of biopropane. And actually, you can reuse it as a source. We have a process called H2Bridge where you can reuse it to make hydrogen. You send that to a SMR, for example. Or some companies actually really interested in buying biopropane. Then you remove the oxygen, but you have 2 routes. So either you produce water, which is the preferred route because you want the carbon to stay in the product. Or you can also go decarboxylation route, where basically the carbon, you make CO and CO2, or CO2 that then with a reverse water gas shift, you have some CO. So, and then you can upgrade your product. Let's say you want to make jet fuel, you need to crack because you've seen the feedstock, it's above, you have a lot of diesel. If you hydrotreat your used cooking oil, you will have a lot in your diesel range, so you need to crack that. And you also need to dewax to improve the cold flow properties. So what can you affect? What can you not affect? Basically, this we can help you with, because this is the rest, that's how it is, it's chemistry. And we cannot prevent that you will lose your C3 and your oxygen. But with the right catalyst, you can actually choose deoxygenation route, which means that the carbon will stay in the product instead of producing CO2 or CO. Then to upgrade, you can minimize yield loss with the proper dewaxing catalyst and the proper hydrocracking catalyst. And I think I have a few slides about that. I'll go quickly. It might not be relevant if you're a student, but maybe if you work in a refinery, that could be useful. So quickly, first route is HDO. So as I said, you produce propane, water, and then, so octadecane, and it stays. I never remember what is odd, what is even. So, but anyway, C18, C20, I think it's even number, stays, the carbon stays in the product. Or if you go decarboxylation route, you produce CO2. And here, this is an example about a catalyst that by basically playing with the right catalyst, you can choose, do you keep the carbon in the product, or do you produce CO2 and CO? Here it's based on a SIMD, so simulated distillation, which is a GC. It's like it's a GC with an FID detector. So basically, you can look at do you produce C17 or C18? So with the first catalyst, you have a mix, a lot of C18 and a lot of C17. So it's mostly HDO, but a bit of the other route. Catalyst B, you produce more, you go to the decarboxylation route, which is not really favored if you want to make to keep your carbon in the product. And the last one, catalyst C, you mostly favor HDO route, which is really good. So basically, by playing with the catalyst, with the right one, you can help. And here I mentioned TK330 and TK340 that are good at that. Dewaxing, you make this beautiful normal paraffin, C18, it's very nice, but high cetane index, we like that for the diesel pool. But the cloud point is actually not very good. It's too high, depending on where you use it. But let's say you want to export to even Southern Europe, Russia, I don't know, you name it, you need to do some cold place in the US, you need to do some isomerization. You need to do some dewaxing. And here you have two ways. So either you move along the carbon. So here, this graph, you have a carbon molecule on the x-axis, and the y, it's melting point of a pure compound. So basically, you can improve by, removing a carbon, but you make your molecule shorter, which means you will make another byproduct, or you do isomerization and you just shift the chemistry of your molecule. So here we take an example of C18, melting point 28. I go hydrocracking route, so I make some C4 and then C14, and here 6 degrees, melting point, really good, but I lost butane. So, or you can go isomerization route, and here you also meet -6 or 6, sorry, and you stay within the same boiling range and you don't have any byproduct. So again, here by playing with the right catalyst, dewaxing catalyst, you can choose this. And here, quickly again, this is a cloud point improvement versus diesel yield loss. To show you, we have different catalysts, sour mode, sweet mode, is it base metal, noble metal, you name it, depending on the configuration, but we have a right catalyst that can minimize yield loss. Okay, Fatima, how are we with time? How much time do I have?
We're doing well. We're doing well.
Okay, cool. Perfect. Thank you. Challenges. Okay, when you will process this feedstock in your refinery, you will have some problems. I won't lie to you. It's not like fossil. Your units were not made initially. If you do a revamp or you want to co-process, those units were not made to process such feedstock. So I listed 4 challenges. Number 1, it's very exothermic reaction. We don't talk about 50 degrees. Let's say you have 100% standalone, so 100% renewable feedstock. Maybe we talk about the delta T of 150 degrees Celsius. And because oxygen are very reactive, they consume a lot of hydrogen. So how do you handle this exotherm? So what we say, we joke often, we say dilution is a solution. So either you can have some recycling, you can also co-process with a fossil feedstock, basically to absorb the heat, or you also have, you can inject at different points. But basically you will have to deal with a massive exotherm, and also you will use a lot of hydrogen. And here on the graph on the right-hand side, you have the amount of renewable feed. Let's say you start at 5%, and you have the additional hydrogen consumption you will use. So basically with 25% more, you are close to 100%. Hydrogen consumption, give or take order of magnitude, it's similar to hydrocracking or higher. We're talking about 400% renewable. It's maybe, I don't know, 300, 350 normal cubic meter per cubic meter of feedstock. It is high. It depends on the feedstock, amount of double bond and so forth, but that's that order of magnitude. So hydrogen is always a discussion we have with customers when a hydrogen production, when we talk about such projects. Do you have enough hydrogen? Then I mentioned quickly a pretreatment in the introduction. Sorry, I'm drinking a bit of water. And why is that? Because I mentioned phosphorus, and you will see a picture in the next slide. But basically, these contaminants might deactivate your catalyst. They will form a crust, and the molecule will not have access to the active site in the pores anymore. So here's an example of a commercial unit. So here you have the exotherm of different catalyst beds. So you have catalyst A, B, and C. And then catalyst A starts really high delta T, and quickly you can see it's fading out. And if you're process engineers, you know what it means when your delta T is decreasing. It's because your catalyst is losing activity. And then interesting enough, catalyst B is taking over to deal with the exotherm. So basically you have a front going down in the reactor, and the reaction is spreading, is happening lower and lower in the bed. And then when catalyst B cannot take it anymore, it's basically deactivated because of this phosphorus crust. Then catalyst C is taking over. And it's really interesting to see this progression of exotherm in the reactor. So that's one of the issues you might have. Number three, it's again to discuss more about this phosphorus. Not only you might deactivate your catalyst if your phosphorus content is too high in your feedstock, if you don't have the right catalyst, but you might also form this. Basically, this is, you need to jackhammer this to unload your reactor. I don't know if some of you worked in a re-refining, so spent upgrading, but that's often a standard practice also because of phosphorus. But basically everything is glued together. So what we did some SEM, scanning electron microscopy of this. So here this is a catalyst particle and another one. And then with EDS, we could basically look at the composition. So we followed that line and said, okay, what is it? What is this light gray basically particle? Is it, we suspect it was phosphorus, and it is, okay. Basically, this light gray, it's mostly phosphorus. It's 25% concentration of phosphorus. So it's a phosphate glass, and the other elements are also sticking to it. Calcium, sodium, potassium, whatever you have will stick to that. It will include the catalyst particle together and make rate pressure drops. We have a solution. We have a catalyst called TK3000 where you have full penetration of phosphorus. So we are solving this. The other solution is to have less and less phosphorus, but you will still have some phosphorus. At one point, you will either deactivate or have pressure drop eventually. So, but that's the nature of such feedstocks. Last but not least, it's about corrosion. So you have three types of corrosion. So acidic corrosion, let's say you have a used cooking oil with a TAN number of, I don't know, 25 acid number. If your metallurgy is not correct, you might have acidic corrosion. Then you form CO2, so you will have a carbonic acid corrosion. And if you have chloride, let's say used cooking oil in your feedstock from table salt, you will have a chlorine-induced corrosion. And here material selection is a key. So even when we do co-processing studies or revamps, like the whole metallurgy study is really crucial because, of course, for pressure drops, you don't want, here's an example of localized acidic corrosion. And here, imagine this happens, this fall on the grading of the catalyst, and then you might create pressure drop. So that's really important. Okay, I will stop scaring you. We obviously have solutions. So you are in a refinery, you want to co-process or process. So what are your options? Option number one is co-processing. Let's say you are 5-10% co-processing rate. Here, you could do, it's rough number, rule of thumb, but you could do just with a different catalyst grading. And the idea is it's so exothermic that you need to control the exothermicity of these reactions. And how do you do that? You start with a low active metal content, and then you increase so you can control this, and more grading, of course, to handle contaminants. But that's basically with a proper catalyst loading, you should be able to handle co-processing. Of course, you need to look at metallurgy, hydrogen consumption, and so forth, but that's just a rough example. Number two, you might want to revamp. So some of the first units we revamp in Prim in Sweden, in Gothenburg refinery, we revamp for, I think, 30% co-processing. It was a Rotel diesel, was in 2007, I think. And this is revamp. So you look at metallurgy, all the pre-treatment of your feedstock, maybe installing the refinery, hydrogen, corrosion, and so forth. So all of this needs to be studied carefully. And option 3, which I see a bit less these days, it's a grassroots to do co-processing, meaning co-processing fossil and renewable. It's also an option, but yes, this is not something I have seen much lately. The other example, which we see most, so I think co-processing is mostly European now, and then the standalone, so 100% renewable, it was mostly the US. Things are changing, of course, and it's general rules. But revamp, you can also revamp unit. You have we have a lot of projects in the US with hydrocrackers that are revamped to be standalone renewable unit to produce HGO and SAF, or you can have a grassroots. And here's a grassroots is maybe the most expensive, but that gives you the most flexibility in terms of feedstock and products. And that's a lot of the projects we are working on in globally are actually looking at this now because people are worried about feedstock and which product to use. So basically, those are your options if you are in a refinery. So Lego, I don't know if you know, but Lego is actually a Danish invention. So if you come to one of our courses, we actually have a Lego game for adults where you basically learn how to load a reactor. But joke aside, this is the different functionalities you would need. You would need guard to handle the contaminants. Then you will need catalyst to remove oxygen. You will need catalyst to do some dewaxing, which is a DW, and then some catalyst. Maybe if you want to make renewable jet fuel, more renewable jet fuel, you can use some hydrocracking catalyst. So basically, you need different bricks, and depending on the feed, the product you want, you will need different of these functionalities. So again, I mentioned it, renewable naphtha, much more interest lately. The first units 10, 15 years ago, people were actually, can we have less renewable naphtha? And now all the petchem industry is really very interested in buying this. Prices change. It could be similar price to HVO. So it's actually good money also to make with renewable naphtha. It's a good byproduct to have. And it can also be reused for other purposes. Renewable jet fuel and SAF, right now very small amounts is produced, but more and more, you might have heard about that if you are following the world of renewable fuels. But this is, HVO was a bit last year, and renewable jet fuel is really what people talk about these days. There will be a mandate coming in EU, possibly announced tomorrow too. And US is talking about it, and globally, a lot of companies also said we want to fly with sustainable aviation fuel. And the last one, renewable diesel, HVO, of course, has a future for it. We know that light duty will be electrified, likely. It's a matter of when, to some extent. But also heavy duty is not likely to run on batteries. So there will be a big demand for HVO until 2030, and we expect it to continue increasing. So basically, you have these different products you might have, hence the process flexibility I mentioned. Here, very simple example of what we call a single stage or sour mode layout. So, okay, is it moving? Yes, so here you have maybe, it's really simple example. You have 3 beds in this reactor, so maybe you have some guards and HDO catalyst, and then maybe some sour mode dewaxing catalyst. So basically here you can make renewable diesel, you have maybe a bit of renewable jet fuel, you made the specs, and it's one of the simpler layout. This second layout called a sweet mode diesel. So here the idea is to minimize yield loss. So you go into sweet mode basically for your dewaxing catalyst, and then so you have HDO reaction, you strip your H2S, and here in this sweet atmosphere you can use some noble metal catalyst, and I mentioned TK9 920 earlier. Very simple hydroflex technology. We can basically we have a lot of different configuration, again depending on the feedstock and the product you want. Fatima, how are we with time again?
I think we'll have to speed it up a little bit.
Yes, I'll quickly. Last poll for you. In EU 27, so 27 member states, what will be the share of renewable jet fuel in 2035? Fatima, do you know how much? It's not a trick question. You might not know because I don't know how much you follow renewable fuel. But do you know how much renewable fuel is produced? Renewable jet fuel is produced now, like globally. And it's okay if you don't know. Like I don't want to trick you. It's
I'll stick with my favorite option, 5 to 10.
Okay, it's actually very little. It's less than 1% of jet fuel is renewable jet fuel now.
Oh, wow.
It's only 150,000 tons per year. So of course you have a few refineries, but one unit was designed for this mostly. And then you have a lot of byproducts coming in, more units now in Europe and also other places. But it's very, very small. Yet the EU has very ambitious targets. So, okay, what do we have? 5, 10, 15, 20%. Yes, okay. I can tell you how many people have answered, 40. That's okay, 5%. Well, the answer is 20%. So basically, in 14 years, the EU wants every departing flight from EU, and that's going to be announced tomorrow. So it's a big day. If you don't know what to do tomorrow, you have to follow this Fit for 55 package. They will announce it tomorrow, and I will show you, I think, in the next slide. This is the mandate, basically. If you can see my screen, basically in 2035. So the goal is that in 2050, in EU, 2/3 of jet fuel use is renewable. 1/3 is a biojet, and 1/3 is, buckle up, e-jet. So green, like syn fuels. And that's why we're also working a lot on e-fuel. I was surprised a few years ago when I started seeing e-jet. I was like, okay. And this is because this mandate will be implemented. So here there will also be need from other refineries worldwide to export to Europe. The US is talking about it, maybe not e-jet, but at least biojet. It's a global phenomenon. So, and on top of this, on the left-hand side, and I might send you the presentation so you might see it, but a lot of member states are going for higher targets. So it's often starts in Scandinavia. For example, Finland, Sweden, Norway, they're going for 30% of jet fuel, and not by 2045, by 2030. So it's really ambitious target. Okay. But jet fuel, renewable jet fuel is not one thing. It's actually, it can be 7 things. And what we do, so those are the different pathways. So it's detailed in the STMD 7566. So it started with actually Sasol was behind this one with a gasification of coal. And then what we do is this, it's hydroprocessing of fatty acids. So you do this HEFA-SPK. And then you have all these other processes. You might have heard about alcohol to jet. You also have a lot of projects with gasification of municipal solid waste. So SAF is not one thing. SAF can be 7 things now, and a lot of new pathways are on the way. So, and also co-processing is allowed, but I won't spend too much time. And I think I have technical slides. Basically, those are the specs of the renewable jet fuel made from fatty acids. So it's called HEFA-SPK. T10 for distillation at 10% recovered should be maximum 205. And then T90 maximum 300. So that's really that kind of narrow spec you have, and that's really important for process design. Flash point, it's similar to the Jet A1, 38, I think, -40, the same for freezing point. And here, interesting enough, maximum 0.5% aromatics. You might form aromatics actually in your process if you don't control your heat properly. So that's really a strict specification. And interesting enough, you need to blend with something that has at least 8% aromatics. So it's a bit contradictory specification somehow. This is an example. So how to produce to maximize, and you will see the process layout quickly. But this is a feedstock you have. So it was a mix of 50% tallow and 50% used cooking oil. You see the fatty acid profile. So a lot of C16, C18 with 1 or 2 double bonds. And so which process could be chosen? It's an example again. This is not, you have many different layouts, but the first reactors here was basically a HDO reactor to remove oxygen. Second one was hydrocracking. Then we had some stripping. It's similar to a 2-stage hydrocracker. Then so you separate your naphtha and your kero, and then you send your kero to isomerization reactor in a sweet mode with a noble metal catalyst. And here you meet on spec, renewable jet fuel meeting the D7566 specification. I'll go back to my first slide, which was chemistry is key. Feedstock, please spend time on the feedstock because that's going to be your bottleneck. And then we have process catalysts out there. We can design more or less for every feedstock you have or every product you want. We might be able to help, hopefully. And okay, last one, Fatima, then I'm done. We have 6 units, 6. I didn't want to do it too commercial, but yet I still wanted to show. We have 6 running references. We started in 2010, and then we announced a lot of units, which is really good. It's happening globally, a lot of type of feedstocks, and yes, that's what I had to say. Yes, Fatima, I can't see the questions, but are there any questions?
Oh, there are questions. There are questions.
Okay.
So if you'd like to summarize with this one.
This is more for later for the conclusion, but I'm happy to answer a question now. So
perfect. So we do have some technical questions, detailed technical questions, and then I can see that most of them are with regards to the feasibility. But let's start with the first technical question. So a question from Muhammad, and he asks, what would happen upon TK 330 catalysts? Heteroatom C bond would only break down, or CC bonds degradation would occur too? I mean, hydrocracking, would it be significant?
Yeah, but it's not, 930 is not a hydrocracking catalyst, it's isomerization catalyst, the zeolite it contains. So it's mostly isomerization, and you have a bit of yield loss due to a bit of cracking, but it's very minor. So it's mostly isomerization, so ring reorganization, but no hydrocracking with this catalyst, with TK 930 or 920, even less. If you want cracking, we have hydrocracking catalyst, and if you want to make jet fuel, we could do that. But if you just want to do isomerization of your diesel, we have a 930 in sweet mode. So sorry, sour mode with base metal, and then in sweet mode with a noble metal. And those two are commercial and have been running in many units for some years.
All right, good. So I hope that answers your question, Muhammad. Moving on to the next one.
Yeah, if not, you can always write to me. This is my email address. Yes.
Silv@topsoe.com.
Yes.
Sweet and simple. All right. Second question. What is the energy consumption to produce a barrel of biodiesel compared to a barrel of normal diesel from fossil fuels?
What people look at, it's a greenhouse gas emission savings. So I didn't do the calculation for energy consumption, but in terms of greenhouse gas emission savings, it's up to 90% savings. You can be carbon neutral, but let's say even with palm oil, you can save 50% greenhouse gas. So because the trick is when you burn CO2 from biogenic in a biogenic fuel, the CO2 you burn in the engine is not part of the calculation because it was CO2 before. So it stops at when you fill your car, basically. Then the CO2 emitted during combustion is not part of the calculation. So you have a fossil fuel comparator, which is in Europe, it's 94 grams CO2 equivalent per megajoule for fossil. And then when you do your LCA analysis, your greenhouse gas calculation, you take feedstock cultivation, pretreatment, process, and you add all of that and you compare to this. So you have different models in Canada, in the US, in Europe, and each model is more or less similar. But you have to save CO2 emission. That's really how it's used. And in terms of energy consumption, I can look into it, but I didn't do the calculation.
All right. Okay, I can see that. Another question from Ali. What could be the drive technology in the Middle East? Because we rely heavily here on, fossil fuels. We have enough quantity. What would be the profit margin for us here?
The profit, I think, is to export to Europe or to the US. This is a profit. That's why joke aside, we see a lot of projects happening outside Europe. People want to export to Europe, but you need to follow all the regulation I mentioned. But the prices are changing a lot. But what is the price of HBO now? I think it's 2,000 euro per ton, something like that. So it's really a lot of, and it's varying a lot. I didn't check the last Argus statistics, but it's really changing a lot. And SAF, it's maybe 3,000 euro per ton. So it's, I don't know the latest numbers, but it's by exporting to countries with legislation, you will, that's a good business case.
Yeah.
If you have the feedstock.
If we have the feedstock. And do you think we do have the feedstock here in the Middle East?
There's some work done in algae, for example, algae production, microalgae, and also some crops that do not need, like these rotational crops or wind crops that I think there was a project with castor oil in some deserted areas because they don't need much water. But it's long term. Maybe in 10 years, this will be implemented. So yes, so it could be. But if you look standard waste oil and fat, there's not much. So it's really 30, 40 million tons per year. So that's as good as it gets. So it's really, you would need new, otherwise waste, you go to municipal solid waste, plastic, and this is a feedstock you have, but you would require maybe pyrolysis, gasification, and Fischer-Tropsch. So it's quite expensive. But you have, if you look at solid waste, if you look at oil-based feedstocks, you would need to go to these specific crops that are not commercial yet at large scale.
Yeah. All right. So are you aware of any plans for new facilities here in the Middle East, or just too early?
So far, I didn't see anything concrete. There was a lot of projects announced. I'm yet waiting to see how, there's a few flagship projects that are maybe running, but it's so far, I think it might come in 5-10 years. But if there's a business case to do for Europe and the US and Canada, and if other countries have really high mandate, Europe alone might not be sufficient to produce. So we do see interest from yes, other countries.
The questions are coming in, so I think we'll be here for a bit of a time, which is good. So co-processing 10%, should we expect hydrogen consumption to be higher or lower than normal?
Higher.
For co-processing.
Yes, co-processing. Each percent, I think I had this graph about, okay, let me go back to it. Sorry. But yes, you will increase by, what was it, 10%? We're around 20% more. Sorry, I have too many slides. That's my fault. You will have, for every percent of hydrogen, of renewable feedstock you will use, due to the oxygen content, you will use more hydrogen. So that's how it is. So let me find it. Sorry, Jesus. Yes, so maybe 10%, you're around, okay. It depends on the amount of double bonds you have in your feedstock, but maybe with 10%, you're around maybe 25, 30, 40% more hydrogen. So you're going to consume more hydrogen for sure, due to the oxygen and the double bonds.
So oxygen has to be available.
Hydrogen, yes, you need hydrogen. If you are short of hydrogen, we have, as I said, actually, we have this process called H2 bridge, when you can recycle renewable naphtha and bio-LPG, send it to a steam cracker to make more. So you make some green hydrogen based off that. But that's a way to minimize your emissions. But otherwise, you will need more hydrogen. Also, why we see a lot of products using green hydrogen, or you will need a lot of hydrogen.
Yeah, see that. All right. Another question again from Ali. What are the current unit licensors and catalyst suppliers for this new technology?
I cannot talk about the competitors.
Yes.
Good question. I can talk about Topsoe, then you Google,
yes.
And you have a few licensors. So we at, I don't want to be arrogant, but we're doing well within this segment. No, but really, like we have a big success. Like we were some of the first runners. In Scandinavia, we're lucky enough to design the 100% unit with UPM in Finland, Prim. So we have a lot of units have been running for many years. So, and in the US, we have, if you check our blog, you would see some of the press release. We can maybe announce just the top of the iceberg of the project, but it's, it's very, and it's global. It started EU and US, and now it's really spreading. So,
yeah. And it's going to grow.
Google, Google, and now you can see who are our competitors.
Topsoe.
Yes.
Let's see. We have technical questions. What are the typical reactor operating conditions?
It's similar to I don't know, high pressure hydrogen. I don't know. It's always a question. We have sometimes people is like, okay, I have this reactor, 30 bar, can I co-process? HGO is actually good, but the dewaxing is the main problem. So I would say if you have a unit at 50 bars, it's good. 50 bar pressure hydrogen. 40 maybe. You need to look at the feedstocks. My colleagues, I can imagine my colleague in tech service rolling their eyes when I say these things. But yes, 50 bar, you're good. 50 up, you're good. 40, good. 30, I don't know. It's we need to look at it. So
that's high pressure.
Yeah.
Hydroprocessing. And what is a typical unit capacity? And could you please give some ideas of the capital investments?
I can talk about the capacity for sure. The capital investment, I will not comment on this. But capacity, so we talk about very small amount, like compared to fossil. So like the unit, the small unit in the world, maybe it's 100,000 tons per year, and the biggest one, 1 million tons per year. So it's really, it's a few thousand. At most, it's maybe a few thousand barrels per day, because the feedstock is really hard to supply. So it's really, we talk about, small, compared to fossil, small units.
Okay.
But let's say you want to revamp, you cannot use the same, you have a unit, you want to run 100% renewable. You will not be able to use the same flow because of the exotherm. So you would need to lower much more and recycle and have some, so yes, but the flows are much lower. We designed a unit for Sky Energy in Holland to produce renewable jet fuel, and I think it's 150,000 tons per year, something like that. So, and the bigger ones are, I think we designed the biggest We are licensing now one of the biggest unit. I can't recall. It's 6,000 maybe barrel per day, 6,500 barrel per day. That would be the biggest worldwide. So it's
a wide range. Wide range, however, still small.
It's we understand because again, feedstock is challenging.
Yeah. Okay. Good. Another question: what percentage of the biojet is derived from waste rather than virgin feed?
Right now, what is it using? Okay, I can talk about what is used now for. If you look at biodiesel. Because I don't have the number off the top of my head. It's in a report, but I don't have it here. So what I can talk about is biodiesel, HVO, and SAF. What is used now, 70% is virgin oil. 40% is palm oil. I think we're around, 70% with palm oil, soybean, and rapeseed oil to make biodiesel, HVO, and SAF. So that's really where we are. So yes. For SAF, the future, I foresee mostly waste. Why? It's because of greenhouse gas emission savings. You will have a target, is it 50, 60%? And it's very hard to meet that saving with virgin oils because if you look at emissions, if you produce, renewable jet fuel from virgin oil, 2/3 of the emission might come from cultivation. So, but if you have a waste, you have no emissions. So you can really meet this target. So I think it will really go toward waste, oil and fats. But again, 30, 40 million tons per year. How? Will be, it's not enough. But that's why alcohol to jet and Fischer-Tropsch also alternative processes because you have a lot of cellulose and municipal solid waste. So it's, yes, you have these 7 pathways and all of them for jet fuel. That's why all of these will play a part. There's not one winning solutions. Everything will contribute.
Yeah,
so.
Good. I think that answers a question from Harry, which says, is jet fuel production from lignocellulosic a biomass feedstock, which is the
not yet. So far, it's mostly HEFA, so hydrotreated esters and fatty acids. So you have a few projects with alcohol to jet and gasification of municipal solid waste, but those are demo stage and they're scaling up. So let's see when they are implemented. But this year and next year, we'll have a larger scale projects.
All right, good. Another question, do you think there is enough feedstock in the world to meet the demand for RED, HVAC, biodiesel?
No, quick answer. Actually, the EU made some really nice report, I think from 2018, it was called Clean Planet for All, and they made a really nice, interesting study about feedstock availability. And if you consider waste, yes, solid waste, we might have enough. Well, actually, I don't know if you might not know, any of you, but we have a podcast on renewable fuels. It's called Fuel for Thought. And season 3, we're preparing season 3, and it's coming after summer. And we have one episode about feedstock. And so we will discuss that with an expert on feedstock supply. It's going to be, there will be fight for, now all the prices of feedstocks are increasing, and there will be a fight. So we believe, of course, there will be electrification, but all the solid waste to fuel will play a part. When? Maybe after 2030, but we need this solid waste to play a part. Otherwise, it's not, I don't think the rotational crops and winter crop and algae can be sufficient. All feedstock will play a part, also virgin oil. But some countries like Indonesia, Malaysia, they have palm oil, so they will use that. In Latin America, soybean will be used. Maybe in Europe tomorrow, they will say that soybean oil might not be good anymore. So it's going to be tough. So my guess, not enough feedstock right now.
Right now. Good. Again, more questions coming in. You can see them like rolling, which is good.
Good.
What is the expected catalyst life in case of 100% renewable used cooking oil as feedstock?
With the right grading, I think it's similar to a fossil because the main source of that, if you have enough hydrogen to prevent coking, and if you control your exhaust properly, if you have the right grading and the right layout, I think would be similar to a standard fossil unit. But you need the proper, it will be about grading. We have, you might have some skimming, maybe if you have a guard bed. Imagine a hypothetical case, you have a guard bed. So similar to spent lube unit, upgrading of spent lubes, you might have a guard reactor that you might at least skim and this, but yeah, it depends on your phosphorus content. If you give me a feed with very low amount, we can have very long life cycle. If it's high phosphorus content, it's 3 years we're pushing it. It depends on the size of the reactor, but how much guard you have. But yes, it can be lower, but if you design properly, it could be similar. But you are likely to have problems when you use renewable fuels. Renewable feedstocks. It's corrosion, feedstock. The supply of feedstock will change. So you need basically to adjust your pretreatment unit properly. You don't want a slip of phosphorus, even if you have a slip of, I don't know, a peak in phosphorus, that's enough to make something. So it's you can, but it's going to be a challenge.
It's heavily reliant on the quality of feed. You can see.
Yes, but similar to, I don't know, maybe it's not the same issue in Middle East refinery, but many refineries in Europe, they get this opportunity crude, whatever they can get. And this creates a lot of upsets. So it's a similar way of approaching feedstock, but you get much smaller batches. So
yeah, so they can blend it in. All right. Again,
co-processing, you will have a longer cycle length for sure compared to standalone.
For sure. Let's see. Question from Taqi. How did they go about producing huge amounts of hydrogen and still have lower overall carbon footprint of production?
Because, okay, hydrogen, so from hydroprocessing, it's actually similar. The emission from hydroprocessing and FEM and aerification are similar. It's around 10-15 grams. So okay, it's going to be Europe. Every megajoule of biofuel from 2021 needs to emit at most 32.1 gram of CO2 per megajoule. So you have 32 gram. That's your maximum. And maybe hydroprocessing or FEM, it's about 10 to 15. Using natural gas to make using hydrogen made from natural gas. So you are below the target already. If you have yes, and if that's why we also have a lot of projects, sorry, on producing low greenhouse gas hydrogen. We have ESMR, so you electrify your SMR, or we also have electrolysis cells, also blue hydrogen. If you minimize your hydrogen, your emissions to produce hydrogen, you can, yes. But basically to answer your question, even just the emission from hydrogen, it's much less than the target of your for your finished product. Did that answer the question, Fatima?
I think you did.
Somehow, okay.
So it's a relative.
Yes, but it's small. It's less, so don't worry.
Good. Question from Greg: do the products derived from waste or even virgin feed require the same additives as fossil fuels, for example, antistatic additives?
I had the same question yesterday from a customer. So I did my homework and then actually, yes, you don't need a biocide or you don't need anything specific. For sync lubricity and you need the same. What I heard once is these core flow improvers do not work because it's very paraffinic. So it's standard problem with additives, but normally it's the same additive you will use for your fuel in your diesel or jet fuel pool. So it's more if it's very paraffinic. So some additives do not work when it's very paraffinic. But I'm not an expert in additives, so you need to ask your provider, but you don't need anything specific. You make normal paraffins, or isoparaffins. So you don't need, to my knowledge, and feel free to write in the chat, but to my knowledge, you don't need anything specific.
Okay, good. It's good to know. The last question I can see here, which is, will Topsoe also provide pre-treatment technology for the UCO as feedstock? So do you have such
we work with all providers of pretreatment. Yeah, many of our projects are with different providers. So we have a list of contacts for all the different pretreatment technology providers. Those are standard technology from the FEM industry biodiesel. So it's really robust. We have a podcast season 2, I think it's episode 4, about pretreatment. It's with Crown Ironworks and Alfa Laval. And we discuss a lot about pretreatment, how much it costs, and what are the tricks. So, but don't go cheap on pretreatment. It's my guess, because then you will have problem with phosphorus and you will kill your unit. And every day of shutdown, you know that more than me, if you work in a refinery, is very expensive. So it's better to work and have a good pretreatment. Pretreatment can go from, if you look at total investment costs, can be 2% to 10-15%, just a pretreatment. So that can be quite an intensive, not intensive capex, but but you don't want to go cheap really. So
yeah.
But these are usual pretreatment companies. We work with all of them.
Okay, that's good. And I think that's all the questions that I can see in the chat box. So if there are any other pressing questions, or if you do have a question that you'd like to ask directly.
Yeah, I put the last slide so you can have my email address again. You can write to me. I'll do my best. I'm on holidays in 2 weeks, so I still have time. And oops, sorry. It's gone. I don't know what you can see now. Yes, apps. Yes, and no, you don't see. Yeah, I cannot go back. Yes, but basically, yes, you can listen to our podcast if you wish. We don't promote our products. Like, it's very technical. We get really good feedback. I think last week we reached 30 or 40,000 downloads. So it's good technical knowledge. So season 3 coming after summer. So you can. We talk about jet fuel, renewable jet fuel. Actually, we talk about certification of biofuels. We'll talk about what else did we talk about? Feedstock supply, and then maybe one about marine. It's not recorded because the marine industry is moving, and I'm not sure biofuel will play a part in that. But we see some activity, especially in Denmark, with all these shipping companies. So let's see. Anyway, so fuel for thought.
I've heard some of the podcasts actually. They're really good. So they're now on my list for driving to work, driving from work, in the car. So
thank you. Cool.
They are recommended.
But okay, stop sharing.
Awesome. So would you like to share any?
Nope, that's all I had. I just wanted Fatima, thank you again for welcoming me, and I hope you got something out of it, listeners. And I don't know you, so it's hard to interact through a webinar. But I'm very happy. If you have any questions, you can write to me again. Or if you don't have my email, maybe Fatima can provide it to you if you're right. But otherwise, yeah, check our website or LinkedIn. I'll do my best to help.
Thank you. Thank you very much, Sylvan. It has been a pleasure to have you here with us tonight. I'm sure everyone who joined us tonight has learned something new. It's a new topic for us, interesting topic. And I can see that a lot of our attendees are from refining backgrounds. So for us to know about these technologies and how you incorporate chemistry and catalyst in it, it is interesting.
You have the right competencies in a refinery. You need to build new competencies, as I said, about legislation, greenhouse gas certification, and all the paperwork, but you have the right units, and it's not, you would know how to do it, but it might come faster than you think. I remember customers in Latin America were like, even Russia, renewable fuels, who cares? Be careful, it might happen quickly. So you never know.
With the legislations that are coming,
it's in Europe. Tomorrow is going to be a big day. I call it a revolution in Europe. Like, it's really going to change the whole transport and energy industry. So I think it's going to be tough for the refineries. So anyway, let's see.
We'll keep our eyes open for tomorrow.
Exactly. Yes. Awesome. Good.
So thank you.
Fatima, thanks again. You are a very good host. I'm really impressed, just so you know. Good job.
Thank you very much, Sylvan. And again, thank you to everyone who joined us here in our LET webinar. We will be hosting these webinars more frequently, where we bring interesting new topics, innovative topics that are of an interest for chemical engineers. So thank you for joining us. The recording will be on our YouTube channel, so Be Chemi. It will be there, it will be available. You can subscribe on YouTube, but you can subscribe on our website so you can receive more newsletters and information about upcoming webinars. And with this, I would like to thank you all, and thank you, Sylvan, for this, and have a good night.
You too. Thank you. Bye-bye, everybody.
See you.